Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is the capacitor discharging process. Our objective is to examine the transient or time-based analysis of the capacitor discharging process. We'll learn discharging capacitors can supply a brief surge of outgoing current, where the duration and intensity of this current surge is determined by the electrical properties of the circuit under inspection. Additionally, we'll learn that during the transient discharge process, voltage across the capacitor drops. This lecture operates under the presumption the viewer is intimately familiar with the capacitor charging process, as illustrated in the capacitor charging lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. You'll recall we ended the aforementioned lecture with a summary of the electrical properties for 3 example capacitor charging scenarios. To keep this lecture short and manageable, let's pick up where these examples left off. In case you don't have your notes, here's what we learned about example 1. Example 1 was a series circuit consisting of a 12-volt source, a switch that closes at time t equals 0, a 200 ohm resistor, and an initially uncharged 15 microfarad capacitor. During the charging process, we learned that it had a time constant of 3 milliseconds. Just so we don't get confused later on, let's call the time constant for the charge phase tau 1. When switch 1 closed at time t equals 0, the transient charge process completed after 5 time constants, or 5 times 3 milliseconds, or 15 milliseconds. Current through the capacitor, IC of t during the charging process, was 60 milliamperes times e to the negative t over 3 milliseconds. Current through the capacitor experienced an initial surge of 60 milliamperes and decayed to 0 amps by 15 milliseconds. Voltage across the capacitor, Vc of t during the charging process, was 12 volts times 1 minus e to the negative t over 3 milliseconds. Voltage across the initially uncharged capacitor started out at 0 volts and grew to 12 volts by 15 milliseconds. Current through resistor 1, IR1 of t during the charging process, also equaled 60 milliamperes times e to the negative t over 3 milliseconds. Current through resistor 1 and all elements in series with it experienced an initial surge of 60 milliamperes and decays to 0 amps by 15 milliseconds. Finally, voltage across resistor 1, VR1 of t during the charging process was 12 volts times e to the negative t over 3 milliseconds. Voltage across resistor 1 surged to 12 volts and decayed to 0 volts by t equals 15 milliseconds. Note these functions are valid only for the charging process between t equals 0 and t equals 15 milliseconds. Let's examine the capacitor discharge process using this same circuit. After 5 time constants, in this case 15 milliseconds, the transient capacitor charging process is ended, and we have entered steady state final conditions. Voltage across the fully charged capacitor will be 12 volts, and current flow will have ceased. If switch 1 remained closed beyond 15 milliseconds, really nothing more would happen whether you kept it closed for an additional 15 milliseconds, an additional 15 seconds, an additional 15 minutes, or an additional 15 years. Beyond 5 time constants, this capacitor will be as charged as it ever is going to get, and you cannot charge it anymore. If we open switch 1 after 15 milliseconds, assuming the capacitor to be ideal and exhibiting no self-discharge, it would still appear as if it were a 12-volt differential across the capacitor, positive to negative, top to bottom. The fully charged capacitor is in effect a reservoir of stored energy, albeit one of limited quantity. While we're on the subject of energy, recall that energy is power times time. Thus, energy delivered to the charge phase would be equal to the area under the power curve, which itself would be the product of voltage times current. Unless you've got a black belt in calculus, this math is a little heavy, so here's a convenient shortcut. The total energy supplied to a capacitor over a complete charge phase would be equal to half the final voltage squared times the capacitance value in units of farads. Energy equals half the voltage squared times capacitance. Because there is a relationship between charge, voltage, and capacitance, one can also solve for total energy stored in the capacitor as the charge squared divided by twice the capacitance. Energy equals charge squared divided by 2 times capacitance. Substituting in our given values of 12 volts, 15 microfarads, and 180 microcoulombs, either formula yields a total energy delivery of roughly 1.1 millijoules. This small quantity of stored energy can be temporarily put to use. Consider the addition of a second switch, an R2, a 400 ohm resistor. Upon closure of switch 2, a discharge path exists through the 400 ohm resistor. So we don't lose ourselves, let's just say we restart the clock at another time t equals 0. I'll come back to correct this assumption after we're complete, and compare and contrast the charge and discharge process with one another. A couple events define the discharge process. Number 1. The quantity of charged particles accumulated on the capacitor plates during the charging process seek equalization through this new discharge path afforded them. Conventional current leaves the capacitor, emanating from the positive terminal, traveling through the 400 ohm resistor top to bottom, and returning via the negative terminal. If we earlier defined current into the charging capacitor as positive, this reversal of current flow out of the discharging capacitor must necessarily be considered negative. You think this is just an annoying detail, but it has real-world applications for instrumentation. Consider an ammeter configured into out, top to bottom, monitoring current into and out of the capacitor. During the charge process, conventional current would travel into out, top to bottom, and the ammeter would read a positive value. As we learned in the previous lecture, this charging capacitor would experience an initial surge of positive 60 milliamperes, followed by a decay to 0 amps after 15 milliseconds. If the ammeter remained in this configuration during the discharge process, really, who's going to take their time to stop and switch positions of the ammeter? The discharge current would travel out to in, bottom to top, and the ammeter would read a negative value. The intensity and duration of the outgoing current surge is temporary and quantifiable by the amount of energy available in the charged capacitor and the electrical properties of the discharge path. These general-purpose plots of current through the capacitor, IC of t, and voltage across the capacitor, VC of t, illustrate the discharge process quite nicely. Discharge current surges to some negative value and then decays to 0 after 5 time constants. Voltage across the capacitor drops from its start value to 0 volts at the same rate. Importantly, during the discharge process, these properties don't instantaneously change, but rather undergo an exponential transition. After the transient discharge phase is ended, we again would enter a steady-state condition in which current flow is ceased, and no voltage would appear across the discharge capacitor. Current through the capacitor can be modeled using this function. IC of t equals negative I times e to the negative t over tau 2, where negative I is the magnitude of initial current surge, and tau 2 is a time constant of the discharge path, defining the rapidity of the discharge process. Voltage across the capacitor can be modeled using this function. Vc of t equals Vi times e to the negative t over tau 2, where Vi is the initial value of the capacitor voltage, and tau 2 is the time constant defining the rapidity of the discharge process. The only data we need to perform the transient analysis of the capacitor discharging process are the specific values for the start points, the end points, and the time constant tau 2. Luckily, all of this information is easily obtained. Perhaps the easiest plot to interpret is voltage across the capacitor as a function of time, Vc of t. For this discharge example, voltage starts at where the charge process ended. We learned in the previous lecture that the charge process ends with 12 volts across the fully charged capacitor. The beginning of the discharge process would therefore start at 12 volt and drop to 0 volts over time. Vi is therefore 12 volts. The magnitude of the initial surge of outgoing discharge current can be calculated using Ohm's law. When 12 volts is applied across a 400 ohm resistor R2 at t equals 0, Ohm's law demonstrates current through the capacitor surges to negative 30 milliamperes, where the negative sign is again indicative of the reversal of direction. The value I is therefore negative 30 milliamperes. The observant among you may note that not only is discharge current traveling out of the capacitor rather than into it, the magnitude of the discharge current surge is half the value we calculated during the charging process. You'll recall we observed an initial current spike of 60 milliamperes during the charging process. Given this reduced rate of discharge current, we might expect the discharge process to unfold at somewhat slower rate than the charge process. Given these easily identifiable start and end points, all we need to do now is to determine the time constant for the transition. This is also pretty easy. Similar to the capacitor charging process, the time constant of the capacitor discharging process is the resistance times the capacitance, where tau 2 equals R2 times C. Substituting our given values yields a time constant of 6 milliseconds. As we anticipated, the time constant for the discharge phase is twice as long as that we calculated during the charging process. The root cause for the longer time constant is obviously the larger resistor through which the capacitor is expected to discharge. Current through the capacitor as a function of time can be modeled as IC of t equals negative 30 milliamperes times e to the negative t over 6 milliseconds, where negative 30 milliamperes is the magnitude of the initial current surge, and 6 milliseconds is the time constant tau 2. The plot of current through the capacitor as a function of time demonstrates it spikes to negative 30 milliamperes and then drops to 0 amps by 5 time constants, or 5 times 6 milliseconds, or 30 milliseconds. Voltage across the capacitor as a function of time can be modeled as Vc of t equals 12 volts times e to the negative t over 6 milliseconds, where 12 volts is the initial voltage and 6 milliseconds is the time constant tau2. The plot of voltage across the capacitor as a function of time demonstrates that it starts at 12 volts and drops to 0 volts by 5 time constants, or 5 times 6 milliseconds, or 30 milliseconds. You'll note discharge current ceases at the same time voltage across the capacitor drops to 0 volts. It makes sense. Given no voltage differential, there exists no charge and no incentive for current to continue traveling. The capacitor is discharged and we enter a steady state at-rest condition where all stored energy in the capacitor has been dissipated by the resistor in the form of heat. Given these functions, one can perform analysis of the transient discharge period at specific points in time. Given these functions, one can perform analysis of the transient discharge process at specific points in time. Let's say we're being asked to solve for the instantaneous value of current through and voltage across the capacitor 3.5 milliseconds into the discharge process. Substituting 3.5 milliseconds into the current through the capacitor as a function of time equation yields an instantaneous value of roughly negative 16.7 milliamperes. Why is it negative? Because we previously defined incoming current as positive during the capacitor charging process, and we're somewhat bound by this earlier decision. In this case, 16.7 milliamperes is leaving the capacitor. Substituting 3.5 milliseconds into the voltage across the capacitor as a function of time equation yields an instantaneous voltage value of roughly 6.7 volts. Let's put these instantaneous values at t equals 3.5 milliseconds to the side for later use. One can also use these equations to determine at which time certain events occur. For example, let's say we wish to know at which time the current spike has subsided to negative 10 milliamperes, 1/3 of its initial value. Negative 10 milliamperes equals negative 30 milliamperes times e to the negative t over 6 milliseconds. What time value in milliseconds satisfies this condition? Divide both sides by negative 30 milliamperes. Take the natural log of both sides. Remove the negative signs on both sides of the equation and multiply both sides by the time constant tau2. We're left with a time value of roughly 6.6 milliseconds, just past one time constant. We can perform the same type of analysis for voltage. Let's say we wish to know at what time the voltage across the capacitor has dropped to 6 volts, half of its start value. 6 volts equals 12 volts times e to the negative t over 6 milliseconds. What time value in milliseconds satisfies this condition? Divide both sides by 12 volts. Take the natural log of both sides, then remove the negative signs on both sides of the equation and multiply both sides by the time constant tau2. We're left with a time value of roughly 4.2 milliseconds. Let's put these instantaneous values at t equals 6.6 milliseconds and t equals 4.2 milliseconds to the side for later use. Other electrical properties can be calculated during the transient discharge process, notably the current through the resistor as a function of time, IR2 of t, and the voltage across the resistor as a function of time, VR2 of t. Luckily, these properties are easily obtained if you've got an understanding of series circuit properties, Ohm's law, and Kirchhoff's voltage law. This is where our earlier sign convention becomes pretty cumbersome. Recall capacitor discharge current is assumed to be negative because during our analysis of the previous capacitor charging process, we assumed incoming current to be positive. We're kind of stuck with this definition. No such previous restriction exists for current through resistor 2 since we haven't measured it yet. During the discharge process, given current travels in to out, top to bottom through resistor 2, let's just go with this convention and assume current travel through R2 top to bottom is positive. Despite the coyness with signs, you'll note current through resistor 2 would still be the same as the current through the capacitor because they are in series with one another. The moment switch 2 closes at time t equals 0, R2 would experience a surge of 30 milliamperes traveling top to bottom, which decays to 0 amps by 30 milliseconds. Current through R2, IR2 of t, can therefore be modeled as 30 milliamperes times e to the negative t over 6 milliseconds. Why is the sign positive rather than negative? Because we're not restricted to some prior assumption as we were with the capacitor. Trust me, all these annoying details will all make sense in a moment when we overlay a back-to-back charge and discharge process on top of each other. Given the capacitor and resistor 2 are the only elements in the discharge circuit, any rise induced by the capacitor must be dropped across R2. VR2 of t equals Vc of t, which equals 12 volts times e to the negative t over 6 milliseconds. Plotted as a function of time, VR2 of t looks identical to the plot of voltage across the resistor. It starts at 12 volts and drops to 0 volts over a time span of 30 milliseconds. One can use these cumbersome time-varying expressions to solve for instantaneous values of current through and voltage across resistor 2 at specific moments in time, or just as easily use series circuit properties, Ohm's law, and Kirchhoff's voltage law. Consider a moment in time at t equals 3.5 milliseconds, when we know capacitor discharge current will be negative 16.7 milliamperes. No calculations needed. We can say at this time 16.7 milliamperes of current is also traveling through R2 top to bottom because they are in series with one another. If this seems too easy, you can always substitute t equals 3.5 milliseconds into our expression for IR2 of t to obtain the same result after much more work. Given the discharging capacitor and resistor 2 are the only elements in the series circuit, any rise induced by the capacitor must also be dropped across R2. If the instantaneous value of voltage across the capacitor at 3.5 milliseconds happens to be 6.7 volts, the instantaneous value of VR2 must also be 6.7 volts at this same time. A simple Ohm's law manipulation supports this conclusion because 16.7 milliamperes of current traveling through R2, a 400 ohm resistor, would indeed experience a 6.7 volt drop. One can also use these time-varying expressions for the resistor to determine the time at which certain events occur. For example, let's say we wish to know at what time the current spike through R2 has subsided to 10 milliamperes, 1/3 of its initial value. Don't make this process hard. Given we earlier demonstrated 10 milliamperes of current is leaving the discharging capacitor at t equals roughly 6.6 milliseconds, this means at t equals roughly 6.6 milliseconds, 10 milliamperes of current must necessarily be entering R2. Similar assumptions can be made for voltage across R2. Let's say we wish to know at what time the voltage across the capacitor will be 6 volts, half of its start value. Again, don't make this process hard. Given we earlier demonstrated voltage across the capacitor at t equals roughly 4.2 milliseconds is 6 volts, this means at t equals roughly 4.2 milliseconds, R2 will also experience a 6 volt drop. In my personal opinion, the discharge process is actually a lot easier than the charge process because there's only two elements involved, the discharging capacitor and the resistor through which the capacitor is being discharged. Any voltage rise induced by the discharging capacitor must necessarily be dropped by the resistor, and any current coming out of the capacitor must necessarily go into the resistor. Really, the only subtle complication involved is our somewhat confusing choice of signs for the directions of current flow, which is an artifact of our earlier analysis of a preceding charge phase. Speaking of which, let's examine a back-to-back charge and discharge sequence. The charge process goes from 0 to 15 milliseconds, and the discharge process goes from 15 to 45 milliseconds. If you want to think of it this way, t equals 15 milliseconds is kind of like the t equals 0 for the discharge process. If you want to, you can add a secondary vertical axis to remind yourself of the switchover. This means any time values we calculated during our analysis of the discharge process must be referenced from this 15 millisecond start point. The charge process is characterized as switch 1 being closed and switch 2 remaining open from t equals 0 to 15 milliseconds, and the discharge process is characterized as switch 1 being open and switch 2 being closed from t equals 15 to 45 milliseconds. Let's consider the electrical properties of the capacitor first. At time t equals 0, the capacitor is initially uncharged at 0 volts. The transient charge process begins at t equals 0 and ends 5 time constants later at 5 times 3 milliseconds or 15 milliseconds. During the charge process, current into the capacitor surges to positive 60 milliamperes and decays to 0 amps in 15 milliseconds. Voltage across the capacitor starts at 0 volts and rises to 12 volts over the same 15 millisecond period. At t equals 15 milliseconds, switch 1 opens and switch 2 simultaneously closes. The discharge process begins. Current out of the capacitor surges to negative 30 milliamperes and decays to 0 30 milliseconds later at 45 milliseconds. Note, current leaving the capacitor is assumed to be negative because of the convention we assigned during the charge process. Voltage across the capacitor starts where the charge process left off at 12 volts and drops to 0 volts 30 milliseconds later at 45 milliseconds. Let's now consider the electrical properties for resistor 1. During the charge process, current through R1 surges to 60 milliamperes and decays to 0 in 15 milliseconds. Voltage across R1 starts at 12 volts and drops to 0 volts over the same 15 milliseconds period. During the discharge process, not a lot happens for R1 given switch 1 is open. Let's now examine the electrical properties of R2. During the charge process, not a lot happens for R2 given switch 2 is open. During the discharge process, current through R2 surges to 30 milliamperes and decays to 0 30 milliseconds later at 45 milliseconds. voltage across R2 starts at 12 volts and drops to 0 volts over the same 30 millisecond period. Several important takeaways should be immediately identifiable. During the charging process, current rushes through R1 and into the capacitor. While charging, voltage across the capacitor rises. During the discharge process, current rushes out of the capacitor through R2. While discharging, voltage across the capacitor drops. Any voltage experienced by resistors R1 and R2 is simply the consequence of the incoming and outgoing current experienced by the capacitor in the charge or discharge process. Importantly, voltage across the capacitor, whether charging or discharging, never undergoes a disjointed instantaneous transition or sudden reversal. That's the point. Capacitors resist sudden changes in voltage and are often employed in circuits that necessitate relatively steady or slowly changing voltage conditions. Additionally, you note the asymmetry of the charge and discharge process. This is a consequence of R1 being a 200 ohm resistor and R2 having a resistance of twice that at 400 ohms. It makes sense that the quantity of energy, in this case 1.1 millijoules, stored in the capacitor during the relatively rapid charge process is expended at a slower rate because of the increased opposition. Thus, a complete discharge takes twice as long. To further highlight this asymmetry, you will note that the current during the relatively rapid charge process is twice that of the relatively slow discharge process. This also makes perfect sense. Current is a measure of the time rate of charge transfer in units of coulombs per second. The complete charge process deposits a quantifiable amount of charges on the plate of this capacitor, where charge equals voltage times capacitance. In this case, 12 volts times 15 microfarads means 180 microcoulombs of charge have been deposited on the fully charged capacitor. During the discharging process, charge transfer rate, i.e. current, is half that we observed during the charge process, and therefore it takes twice as long to get the same 180 microcoulombs of charge off the plates. It makes sense. Finally, if you're ever asked to perform instantaneous analysis of a back-to-back charge and discharge scenario, you need to remember that the discharge process's beginning point, i.e. its time t equals 0, is referenced from the end of the previous charge state. For example, we earlier determined that discharge current will have decayed to 16.7 milliamperes at the discharge phases t equals 3.5 milliseconds. This means the actual time for the larger circuit would be 15 plus 3.5 milliseconds, or 18.5 milliseconds when viewed on the complete timescale. Like I said, it's often helpful to include an additional accessory vertical axis indicating when the charge process ends and the discharge process begins. All you got to do is stay organized. If another charge and discharge process repeated itself from 45 to 90 milliseconds, followed by yet another sequence from 90 to 135 milliseconds, the plot for voltage across the capacitor would look something like this. When the capacitor charges, voltage across it rises. When the capacitor discharges, voltage across it drops. What you get is this quasi-pulse-like DC voltage that never suffers a jarring instantaneous transition or sudden reversal. Moving on, let's get some practice examining the capacitor discharge process using a circuit based on our previous example 2 from the capacitor charging lecture. Recall that example 2 featured a simple series circuit consisting of a 24-volt source, a switch that closes at time t equals 0, a 500 ohm resistor R1, and an initially uncharged 47 microfarad capacitor. During the charging process, we learned that at a relatively long time constant of 23.5 milliseconds. Just so we don't get confused, let's call this tau 1 for the charge phase. Here's what we learned about the charge process from 0 to 117.5 milliseconds. IC of t during the charging process was 48 milliamperes times e to the negative t over 23.5 milliseconds. Current into the capacitor experienced an initial surge of 48 milliamperes and decay to 0 amps over 5 time constants or 117.5 milliseconds. Vc of t during the charging process was 24 volts times 1 minus e to the negative t over 23.5 milliseconds. Voltage across the initially uncharged capacitor started out at 0 volts and grew to 24 volts by 117.5 milliseconds. IR1 of t during the charging process also equaled 48 milliamperes times e to the negative t over 23.5 milliseconds. Current through the resistor and all elements in series with it experiences an initial surge of 48 milliamperes and decays to 0 amps by 117.5 milliseconds. Finally, VR1 of t during the charging process was 24 volts times e to the negative t over 23.5 milliseconds. Voltage across the resistor surges to 24 volts and decays to 0 volts over 5 time constants or 117.5 milliseconds. Note these functions are valid only for the charging process between t equals 0 and 117.5 milliseconds. Given these plots, my simple first question to you is this. What happens if we continue to charge the capacitor beyond 117.5 milliseconds by keeping switch 1 closed until t equals 150 milliseconds? The somewhat surprising answer is absolutely nothing. By 117.5 milliseconds, the capacitor is as charged as it's ever going to get, and even if you held switch 1 closed for an additional 99.5 days, it's not going to charge up anymore. From 117.5 milliseconds on to 150 milliseconds, voltage across the capacitor remains 24 volts, and current flow remains 0 amps. This is a steady state period in which conditions have stabilized. Let's include another switch, switch 2, and another resistor R2 at 200 ohms. Here's the setup for this back-to-back charge and discharge scenario. Switch 1 closes and switch 2 remains open from t equals 0 to 150 milliseconds. At t equals 150 milliseconds, switch 1 opens, and at the same time, switch 2 closes. Let's now examine the discharge process by making this an interactive exercise. At t equals 150 milliseconds, switch 1 opens and switch 2 closes. First task. See if you can calculate the time constant for the discharge phase. This should be relatively easy. The second task, however, is a little more challenging. See if you can draw general purpose plots for voltage across the capacitor as a function of time, current through the capacitor as a function of time, voltage across resistor 1 as a function of time, current through resistor 1 as a function of time, voltage across resistor 2 as a function of time, and finally current through resistor 2 as a function of time during the discharge process. To make this back-to-back analysis relatively easy, my advice is to simply assume the discharge phase begins at another t equals 0, and then just superimpose these plots onto the earlier diagrams at the larger circuits t equals 150 milliseconds. Again, we're just looking for general purpose plots for the discharge process right now. Don't worry about deriving exact expressions. Does voltage go up or does it go down? Does current flow in one direction or does it flow in the other? Does current even flow at all? See if you can plot out the general behavior of the charge, steady state, followed by the discharge process. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following conclusions.